In this video we are going to take the pH of a strong acid, which I've noted here is very easy, and then we're also going to take the pH of a weak acid. And understanding the difference between a strong acid and a weak acid is what constitutes two different procedures. So if what we're going to do is calculate the pH of 0.45 molar hydrochloric acid. If we remember what a strong acid is, this is a covalently bonded molecule. When this is dissolved in water, the bond breaks here, and this is not a very strong bond, so the bond is relatively easy to break, and 100% of the molecules dissociate, leaving behind the hydrogen ion, H+, and the chloride ion. So because there's 100% dissociation, that means this reaction only goes to the right. There's no reverse reaction, which means there is no equilibrium set up. And that makes the pH calculation very easy because one molecule here makes one hydrogen ion. So the concentration of the acid is equal to the concentration of the hydrogen ion, or the hydrogen ion concentration would also be 0.45. So the pH here would be the negative log of our H+ concentration, which would be the negative log of 0.45. So we just plug that into the calculator, and we just take the negative log with the minus sign, negative log of 0.45, enter that, and we get a low pH, which is what we would expect. So the significant figures are a little odd. Two significant figures in a concentration result in two decimal places here for the pH. So I'll round 0.346787 up to 0.35, which is consistent with an acid. Okay. Almost all of the strong acids are monoprotic, meaning there's only one hydrogen ion there. So hydrochloric acid, hydrobromic, hydroiodic, nitric acid, HNO3, perchloric acid. Notice these all just have one hydrogen in the formula. There is one acid, sulfuric acid, that's got two hydrogens in the formula. We're still going to treat this when sulfuric acid dissociates in water. The first proton comes off 100%. So we're left with HSO4, hydrogen sulfate, as the ion. So one of these is going to make one hydrogen ion. Now, hydrogen sulfate could act as a base, which it really doesn't because this reaction does not run backwards. But hydrogen sulfate is the conjugate base of this acid. But this also, because it has a proton, can act like an acid. So sulfuric acid is kind of an exception to the rule, but it's not really going to matter. We're going to look at a chart here in just a minute. So the first proton comes off, we have 100% dissociation, no equilibrium here. When the second proton comes off, this is an equilibrium reaction. And if we look at the appendix tables, if we look for any of these strong acids on that table, we're not going to find them. So hydrochloric acid is not on here. Hydrochlorous acid is not the same as hydrochloric. So we see hydrofluoric acid, HF, that's a weak acid. We'll come back to that later. But HCl, HBr are not on here because these are equilibrium constants, assuming that we understand that there is an equilibrium when this acid dissociates. So if we look down here at sulfuric acid, you see sulfuric acid here, the formula, and under the K1 value, when the first proton comes off, this says strong acid. That's because that reaction goes all the way to the right. When the second proton comes off, we see this. And all of that is not important. So even with sulfuric acid, when that first proton comes off, if we want to calculate the pH of, let's say, for example, 0.15 molar sulfuric acid, we're still going to assume that the hydrogen ion concentration is the same as the concentration of the acid. We're not going to worry about this reaction that's going on. So the pH of this would be the negative log of 0.15. So if we do that on the calculator, we have negative log of 0.15, and enter that, and we get 0.82. Again, a low value for pH, which is what we would expect for an acid. What we're going to do next is calculate the pH of a weak acid. And when we look at a weak acid, we're going to have to write the equilibrium. Well, we should show that, so we'll show two arrows. And then we're going to set up the table and then look at the equilibrium value for that dissociation. So I'm going to look at HF. So the weak acid, hydrofluoric acid, we know it's a weak acid because it's on this table. So the aqueous equilibrium constants, again, everything here, this is also called the dissociation constant. So there's an equilibrium set up. That means some of the H plus could react with water and make the intact molecule. So this is what makes a solution acidic. Not having an H in the formula, but having that hydrogen dissociate from the molecule, leaving behind an H plus. So if we look at hydrofluoric acid on the table, its equilibrium constant is 6.8 times 10 to the minus 4th. So for that will be the Ka we'll be using, 6.8 times 10 to the minus 4th. And it's helpful to write the reaction for this. So a weak acid, and we don't need to write the water with an acid, but we could. I'll probably show both. We'll have some H plus and fluoride ion minus. And if we think about setting up a table of initial conditions, let's say that we're going to calculate the pH of 0.45 molar HF. We might be tempted to say, well, it's going to be the same thing as 0.45 molar hydrochloric acids. When we're done, we'll come back and compare. So if we look at this table, we're starting out with 0.45 molar, and we lose an amount X, and here we gain the same amount X, and we gain an amount X over here. So at equilibrium, our HF is 0.45 minus X, our H plus is X, and our fluoride ion is still X. And then if we write the equilibrium expression for this, K equals, I'm going to have the product of the product of the products over here, H plus F minus, over the reactants. So remember, the equilibrium is always products over reactants. And then we just substitute in our equilibrium. And K, we're going to find this in the appendix. So that value we said from the appendix was 6.8 times 10 to the minus 4. Now if we substitute those values in, X is substituted for h plus and also for f minus. And then the denominator is going to be 0.45 minus x. And what we're going to do, this is still a relatively small value compared to some of these values in the table. So 10 to the minus 9th, 10 to the minus 11th. What we're going to do is assume that since this is a relatively small value, that 0.45 minus a really little number is still approximately 0.45. So we're just going to make this simplification and make the math easier. So we're going to say that this is still approximately equal to 0.45. That the small amount that we lose does not affect that concentration. And all it does is make the math a little easier. So this 6.8 times 10 to the minus 4. And then now what we're going to do is solve for x. And it's important when we have a weak acid to remember x is equal to h plus. So once we solve for x, then we're going to take the pH of that value. So if we solve for x here, we know that x squared is going to be 6.8 times 10 to the minus 4th times 0.45, or x is going to be the square root of all of that. Okay. So when I'm solving for x, just so I don't forget to take the square root, I'm going to start out with that. Have the square root symbol. So I'm going to take the square root of 6.8 EE negative 4 times 0.45. So I get x is equal to 0.017 and so on. I am not going to simplify this. I'm going to take the pH of this. So pH is going to equal the negative log of 0.0175. I'm going to leave this number in the calculator. So I'm writing this down just to show what's happening. When I do this, I'm going to take the negative log, and then I'm going to hit the second key and this key down here that's the answer key. So I'm going to take negative log of second answer so that I don't have to round this number. So I take negative log of my second answer, and I get 1. We'll round that to 76. And again, if we have two significant figures in a concentration, we're allowed 2 decimal places as far as significant figures go. So the pH here is 1.76. And this was the same concentration as HCl. So this is higher than the 0.45 molar HCl. And that should make sense, because a weak acid means we have less than 100% dissociation. So we automatically have less hydrogen ion in solution. And if we would have worked this out the other way, and we would have had to do a little bit of algebra here. So if we did not make this simplification right here, that we could say 0.45 minus x was still approximately 0.45, we'll do that calculation really quick. This equals x squared over 0.45 minus x. So you would have to multiply the numerator over here by this and distribute this and probably use the quadratic formula, which I hope I have plugged into my calculator. So 0.45 times 6.8 EE negative 4. So this first number is 3.06 times 10 to the negative 4th, and that's going to be minus 6.8 times 10 to the negative 4th x equals x squared. So I just did the distributive property here. Now I'm going to put all of my terms on one side. So x squared is positive. I'm going to move this over. This will be plus 6.8 times 10 to the minus 4x minus 3.06 times 10 to the minus 4 and set this equal to 0. So I'm going to find the roots. I'm going to find the values for x that make this equation true. So a equals 1, b equals 6.8 times 10 to the minus 4th, and c equals negative 3.06 times 10 to the minus 4th. So when I plug that into the quadratic to solve for x, I'm going to get a value relatively close to this. Now, pH calculation might be off just a little bit because we made this assumption here, which makes the math easier. So we'll see how far off we are. So I program, execute the quadratic, and I've got that programmed in. A equals 1, b equals 6.8, EE negative 4, and c is negative 3.06, EE negative 4. And I solve for that, and I still get x equals 0.0715. I'm not going to use the negative value here. 21715, 1596, as opposed to the value I got here. So if I take the negative log of this number, I've got to do that separately. So I take the negative log of 0.017156, 1596. If I do that, I'm still going to get 1.7. Now it rounds up to 1.77. So doing the math meticulously gives us a pH value where we're off in the 1/100th place. So, in my opinion, I'd rather make this assumption here. So, we don't have much of a difference there. But when we have a weak acid, we're always going to have a 1-to-1 relationship between the acid and the hydrogen ion. And so we'll almost always end up with an x squared term here. So we need to solve for x, which is going to be the hydrogen ion. And once we have a value for x, we take the negative log of that number. And here, the pH, this is the pH of hydrofluoric acid. Remember, the pH of the same concentration of hydrochloric acid was 0.35. So we can compare that to the previous slide. We took the pH of 0.45 molar hydrochloric acid and it was much lower. So the pH for HCl was 0.35. And so by comparison, a weak acid is going to be less acidic than a strong acid.